Today, today we are going to learn definite integration. Definite integration is very much important because definite integration has a lot of applications. Um, in the previous class, we learned antiderivative. Antiderivative explains basics of integration. Now the definite integration is the next class after antiderivatives. Okay, so first of all I have to introduce a concept here which is called a Riemann sum. Riemann sum is something like this. Give me a second. Riemann sum is something like this. Let's say you are given a piece of paper which is having an irregular shape. Now you have to compute the area of that piece of paper, which is hard because it has irregular shape. Here you can just do something like this. Let's say this is the piece of paper given to you. So you could do something like this. You can just tear this piece of paper into stripes. So you take a scissor and then make cuts like this. They should be straight. You make cuts like that, and then what you do, you just compute area of each of these stripes. Let's consider that stripe. You can consider that stripe is a rectangle. If you just ignore this curvature at the top, if you just ignore the curvature at the top and curvature at the bottom, and just treat the top and bottom as straight lines, so that will be a rectangle. So you know how to compute area of this rectangle, which is height multiplied by the width. All right, height multiplied by the width, which is W. So that will give you the area of this stripe or the rectangle, and then you just add all such rectangles together. All right, you add all such rectangles together. That will give you the area of this piece of paper. Actually, that is an approximation. That's a good approximation for the area of this piece of paper. Otherwise, you have a hard time. If you're gonna compute the area exactly, that is very hard. So this is a good approximation. All right, so that is actually called Riemann sum. All right, so let's me introduce that. So let me delete this for now. Riemann sum, the first bullet point, the definite integration is introduced using the Riemann sum. Okay, so you use Riemann sum to define definite integration. Okay, so keep that in mind for now. When we go forward in this class, I will explain how it is done. First of all, let's consider this plot. Let's consider this function. Let's say this is A, that is B. Let's say I'm going to compute that area this area is A. Alright, so I'm going to compute that area. This function is f of x, and this variable is x. Like I explained you before, I can just use the approach cutting into stripes. And so I have this function here. And then it goes like that. Here you have A. I'm sorry, it should go further. Like that. This is your B. And then what I would do, I will just make stripes. Here you see a wide stripe, but normally you have to make tiny stripes. To show, I will make a wide stripe to show everything. So let's say this is AI. That is the stripe I cut. I make plenty of such stripes. I take a scissor and then I cut vertically. So I get this, like I explained in the previous example, where you cut a piece of paper. All right. This is the approach of Riemann sum. Let me introduce Riemann sum here. This is the motivation for Riemann sum. All right. Then go to the next bullet point. All right. So as I explained you in the in that piece of paper example, you know this sum can be used to approximate the area. So here I write Riemann sum can be used to approximate the area between, actually the area here is A, and let me write A, area A between f of x and the x-axis. All right, so that's how we use a Riemann sum. All right, let's go into deep of this problem. The next bullet point, as I explained in the piece of paper example, you treat these are as rectangles. All right, so you treat this top is flat. Okay, so you don't have a problem with other boundaries because this is already flat, flat, flat. The only problem is the top. So you consider the top is flat. If the top is flat, then that's an easy computation, which is the area of this rectangle. So you compute that area, and then you keep on computing area of all such rectangles, and then just sum them up. So that will give you an approximation for this area, which is between the function f of x and the x-axis. All right, so let me redo that. All right, good. So go forward, compute AI by treating AI as a rectangle. All right. Let's say your I goes from 1 to n. All right, so that means you make n stripes. All right, you make n stripes. I will explain how this n comes later. For now, just consider you make n stripes. Then you write your A equals the summation of all those AIs, right? You use the sigma notation to denote the summation. You know this. Sigma is used for summation. So this is extra is the sum. All right. Use sigma to denote sum. I goes from 1 to n, n means you make n such sums. All right, you make n such sums. And go forward, and A equals, now I'm gonna show you something very interesting. All right, so you know that, wait a minute, I made a mistake here. It's a typo. Let me correct that. Actually, this is not equal, you know that, right? So this sum, the rectangles, when you add these areas of rectangles, you don't get this, you don't get that area exactly. If you add all of these, you don't get that area exactly. What you get is an approximation. So let me write that. All right, what I want to say is, this is not equal, that should be an approximation. Okay, it should be an approximation. So this is not equal sign. Oh, my approximation symbol is so weird. Let me rewrite. All right, so that's an approximation. Keep your eye on that. This is not equal, an approximation. All right, an approximation. Now what I'm going to do is, I need the equal sign. I need the equal sign between these two terms, that term, this term. So how do you get that? Now, starting from this approximation, I'm going to estimate it exactly. For that, you have to do small magic. For that, you can use your knowledge in limits. You learn limits in calc. 1. So you're going to use that knowledge here. This is definite integration that you learn in Calc 2, but whatever you learn in Calc 1 is also important for this course. All right, so Calc 2 depends on Calc 1, Calc 3 depends on Calc 1 and 2, some schools are having Calc 4, in that case Calc 4 depends on all the previous calculus classes. All right, so here I'm going to use limits that you learn in Calc 1. So you write this to be limit n goes to infinity of this sum. All right. The meaning of this limit is, let me write the meaning of this. The meaning of this, if you just express this by words, this says make infinitely many n's. This says n goes to infinity. This says this n goes to infinity. I'm sorry. This says this n goes to infinity. That means you are just not computing, you are just not making n stripes. No, not n stripes. You are making infinitely many stripes. Okay, practical, this is what is explained by that. You are making infinitely many stripes, but you are not making infinitely many stripes in practice. What you do is you make n stripes for a given variable n, and then finally you get the limit. That's how the limit works. You know that from Calc 1. Sorry, go back. This is same as saying we make the width of these stripes very small such that the area fits with infinitely many stripes. That's what explained here. All right. Right, let's go to the next bullet point. All right. Now also I'm going to use a little bit of prior knowledge. You know that area under a curve is given by the definite integration. All right. So let me write that here. We know that the area under a curve is given by the definite integration. All right. That means the area under this curve, which is A, okay, the area under this curve is A, you know that already. You know that A already, that's given in this equation. So the area should be this. Oh, sorry. Limit okay, this is same as this area is same as the definite integration. In the previous day class, I introduced the definite integration. All right. If you can remember how do you denote the definite integration, I'm going to give you a quick note here. You write this as this. I'm sorry, I forgot to put dx here. All right, so this is how you denote definite integration. This is called the lower bound, and that is called the upper bound. And this is called the integrand. And that is the variable of integration. All right, so let me put this into a box because that is extra that you learned in the previous class. The previous day note, that is antiderivatives. That's also available on YouTube. All right. Now we go ahead and learn properties of definite integration. Let's go ahead and learn properties of definite integration. Oh, I need blue. Properties of definite integration. These properties are very important because you need these properties whenever you do problems. There are 7 properties. These are not all properties. I'm just stating out only important properties, key properties. I'm planning to state 7 properties here. First of all, let me to give this information. If f and g are two functions integrable over a comma b, close intervals. All right, so you have to keep that in mind. Or if and g should be integrable before defining these properties. Then you can go to the first property, integration from a to b f of x dx equals negative integration from b to a f of x dx. All right, great. That means no harm, you can just switch the limits. All right, without any harm you can just switch the limits. See here, the switch limits are switched. This limit gone there, that limit came here. But the thing is, if you switch the limits, you have to introduce a negative sign. You have to introduce a negative sign. All right. Second property, give me little time, so I'm going to insert. Let me take this little down. Great. Next property is integration from a to b. I'm sorry, it should be a to a. Integration from a to a f of x dx should be 0. All right. Let me explain this thing by using that area example. Let's say you have this curve, and you know this quantity is related to the area. Okay, but the problem is here you start it starts at a and ends at a. All right, so you don't have a proper area like before. You don't have a proper area like here. Okay, you don't have a proper area like here. What you have is just a straight line. All right, just a straight line. So what's the area of a straight line? Area of a straight line is 0. All right, so that's why you get 0. All right, so this is related to that. And then move forward. Third property. In the third property, we're going to learn splitting of two functions. Let's say you are going to integrate two functions from a to b. Integration from a to b, the first function is f of x, and then you have some plus or negative here, and then you have the second function right there, and then you have the integration symbol here. This is same as integrating each function separately. You could integrate fx separately, and then you could integrate gx separately and then apply the arithmetic between. Whatever arithmetic here, you should have that arithmetic here. All right. If this is a sum, that should also be a sum. If this is negative, that should also be negative. All right. Go to property 4. Or if you need to explain this by the area example, that is easy. This is same as, let's say you have this curve, this function, okay, which is f, and you have now that function. Let me make this little bit bigger. Let me redraw it. Let's say you have these two functions. The first function is here, which is not much tall, and the next function is there. And then once you add these two functions, let's say you get that. All right. So the below is, let's say, f of x, that is, let's say, g of x. Then there should be f of x plus g of x. All right. This rule says either you just add these two functions and then get that area at once. You can get that red area, which is right here. You can directly get the red area. All right. Or you can just separate them and then integrate separately. If you integrate that part, you get that area, which is that, and then you integrate this. Which is that, and then sum them up. Okay, you know, red equals yellow and green. So you could explain that by the graph. Go forward for the fourth property. In the fourth property, let's say you are given something like integration from a to b c times f of x dx. Okay, c is a constant here. Keep that in mind. C is a constant. I will mention it later. So if c is a constant, you can take this c out. You don't need to worry about that. You can simply take it out from the integral and then integrate the rest. That is the function where c is a constant. All right, c is a constant. So this is also be explained by the area example, but I don't spend on time on that. You can understand that, so you can do it. You can do it by yourself later. So let's go to next property, which is property number 5. Fifth property, you have something like integration from a to b of f of x. All right, you're going to integrate that function from a to b, but the thing here is, let's say you have a point between a and b, a point between a and b. Let's say the point is c here. Okay, so you integrate from a to c f of x dx, plus you integrate from c to b f of x dx. All right, this argument can be drawn here. That can be easily drawn in this area approach. Let me draw this function right here. I make it less taller. Let's say this is x, that is f of x, and you have this function. All right, and then you have a here, and then you have b here. Luckily you have another point c. Okay, let me mark point c between a and b. It is not necessary to have c between a and b. You can have c outside of a and b, but for convenience I mark c between a and b. Okay, this explains the integration of the entire function from a to b, that is this area, and this explains integration from a to c, that area, and then this explains that area. All right, so you know that red equals green plus yellow. All right, go forward. Then sixth property: if f of x greater than or equals g of x, then you have this property: integration from a to b f of x dx greater than or equals integration from a to b g of x dx. All right, so this can also be explained by this area approach. Now let me draw a function here. Let's say this is x, and you know that f of x is greater than g of x. Let's say this is g of x, and let's assume that is f of x. Okay. This is a, and that is b. Sorry, this is f of x, because f of x is always greater than or equal to g of x, and this is g of x. And now mark the areas. The red area is right here, which is under f, the curve f. All right, and then mark this area, which is under the curve g of x. All right, so that means always the red area is greater than or equal to the area marked by green. So the red area is always greater than or equal to the area green. All right, so that is that property. Move to property 7. property number 7. If f of x greater than or equal to 0, then this integral is also greater than or equal to 0. Right. Here what I'm explaining is, if the function is above the x-axis, let's say you have this function which is above the x-axis, it can touch the x-axis or above or touching the x-axis. All right, so let's say this is your f of x, which is always either touching the x-axis or above the x-axis, and then you consider this area from A to B is positive. You consider that area. What I'm saying is, this area is always greater than or equal to 0. Okay, that never be. What I want to say is, if the function is non-negative, the area is non-negative. All right, so that's clear. And then let's move to examples. So you know all these properties now, which are very important when you solve problems. There are 7 properties. We just explain each property when we do examples. Let's move to the first example. These are very simple examples. I got these examples to explain you the basics. I know most of you know how to do integration, because this part is learned in your high school. The integration, most of the integration is learned in high school. So this is kind of a review for those people. All right, example number 1. Integration from 0 to 1, 4 plus 3x square dx. All right, now we have to go step by step. The first step you could use is you could use property number 3. Here you can see there are 2 functions. The first function is 4, the next function is 3x squared. So you could use this property number 3, where you can split these 2 functions and then integrate separately. All right. All right, so you split that. You write this as, you split the first integral from 0 to 1 for dx, and then the sign in between, which is plus, integration from 0 to 1 3x square dx. All right, and then what is the next property to be used? The next property to be used is, this is a constant, you see, the property number 4. In property number 4, C is a constant, so you can take C out. Okay, you can take that C out. Let me erase that. So you take 4 out, and then you integrate 1 with respect to dx, 0 to 1. In the next case also you can take 3 out, and then you integrate x squared. All right, now you have to use integration formulas. Okay, the only formula you use here is the power law. Power law. If you can remember the power law, I'm going to write it right here. Let's say you have x to the power n. Then if you use the power law, the solution for this one should be x n plus 1 over n plus 1. All right. And you have to make sure that this n does not equal to minus 1. Okay, n can be minus 1. All right, you use that law here. Here 1 is actually x to the power 0. You could write this 1 as x to the power 0. All right. That means here you have 4. This is x to the power 0. If you use this formula, you have x n plus 1. N was 0, so it is 0 plus 1 is just 1. So here you write x 0 plus 1 over 0 plus 1 plus 3 here, x 2 plus 1, 2 plus 1. All right. And thereafter you have to apply these limits. Let me delete this. All right, now you have to apply the limits. Normally after integration I just write limits like this. That's my way of writing the limits. Okay, your way might be different. So I introduce these square brackets and then I just mention the limit like that. Let me keep a small space between. All right. Then I'm going to apply the limits. First I have to apply the upper limit. So it is just 1 minus 0. And then here this is 3 over 3. If you apply the upper limit, 1 to the power 3 minus 0. So the solution is 4 plus 1, which is 5. Okay, so that is example number 1, and just move to example number 2. Let's say this integration from 0 to 1 f of x dx is 17, and integration from 0 to 8 f of x dx is 12. Okay, so you are given these two information. Then you have to find integration of f of x dx from 8 to 10. Okay, so this is the problem you are given. So you are given two integrals. You are given that integral and this integral. Then you have to find that integral. Okay, then you have to find that integral. So how do you do that? All right, how do you do that? Function f of x is not given to you. You don't know what function f of x is, but this problem gives you the entire integration. And then you have to do some kind of simplification to get the integral of f of x from 8 to 10. Okay, let's do this problem. For that you can use a property, one property directly. Okay, let's see which property you are going to use. I'm going to use this property. I'm going to use that property. That property is very important here because that property helps me to split the integral into two parts. All right. So let's consider how these numbers vary. So you have 0 here, and then you have 8, and then you have 10. Okay, so I take this to be A, take that to be C, take that to be B. Okay, so I'm going to rewrite that property. The property is right here. I'm going to rewrite this property number 5. We know integration from 0 to 10 f of x dx equals integration 0 to 8 f of x dx plus integration from 8 to 10 f of x dx. All right, you know this quantity already, which is 17. You know that quantity already, which is 12. And then this is what you have to find. This quantity is just an unknown. All right, so for that you can just do simple simplification. That integral is actually 17 minus 12, which is 5. All right, so that's a very easy problem. All right, now let's move to the third example. Example number 3. Find a integration of g of x, integration of g of x from 0 to 2, and part B, integration of g of x from 0 to 4. Now I'm going to give you g of x. Actually, g of x is given as a curve. It's a drawing actually. So I'm going to show you the drawing. So the drawing is like this. I have to draw it to the scale, otherwise you won't be able to do this problem. So I will take a little bit more time to draw this into scale. So this is 4, 2, 0, minus 2. Alright, this is 2, 4, 6, 7. Let's say that is x, and this is g of x. The curve goes like this. There's a straight line from here to here, and then there's a semicircle. I'm bad drawing semicircles. Give me time. It goes through that point, and then let me try again drawing a semicircle. Okay, good. And then from here to here, it is just a straight line. All right. So this is the curve given to you. All right. it is drawn into scale. Now we have to find these two quantities. Part A, give me a second. Part A, you have to integrate g of x 0 to 2. Here 0, here 2. The integration of function is actually that area. Okay, that is part A. Let me use a different color. That is part A. Now what you have to do, you have to simply find the area of that triangle. The area of this triangle is half times base, the length of the base, multiplied by the height, which is 4. Alright, which is very easy. Now go to part B. In part B, you have to integrate it from 0 to 4, g of x dx. Alright, now you have to integrate from this point to that point. Okay, you can see it has two pieces now. It has two pieces. The first piece is this triangle from 0 to 2, and the next piece is this from this 2 to 4. Alright, so I'm gonna split this into two problems because the curve changes at 2, at x equals 2. So I'm gonna split this like 0 to 2 g of x dx plus from 2 to 4 g of x dx. Okay, this part is already found in the previous in part A. This is already found, which is 4, and the other part is you have to compute let's use green. You have to compute that quarter circle. It's a quarter circle now. Alright, so that is this green, and this is that red. Now let me take this out. This is that red. Now you should remember how to compute area of a circle. If you have a circle, the area of this circle is actually A equals pi r square. Okay, that's the formula that you can use to compute area of a circle, which is pi r square. Now it is not a square, it's not a complete circle, it is a quarter circle. So here you write 1/4 and the area of the circle, which is pi, then the radius. This radius is r equals 2. Okay, that is 2 square. So this is actually 4 plus pi over 4 multiplied by 5, which is 4 plus pi. So 4 plus pi. So that is that area. All right. So in today's class, at the beginning, I introduced definite integration. For that, I use Riemann Sum, which is a very useful concept. And then I explain you like you can just compute the area by just making stripes and then summing up those stripes by treating each stripe as a rectangle. That area equals to the definite integration of the function, which is given inside this green box. And then I explain you 7 properties which are very important, and you have to keep in mind that these are not all. There are some properties. All right. and then I explained three diverse examples. So that is the end of definite integration. Thank you very much.